The aim here is not for us to become the expert in programming assembly language. The aim is that we understand the instruction a little bit more, because later on we will study how we construct the processor such that it executes this instruction. Therefore, we first have to understand the instruction. Okay. In historically, around 1970, there are vast variety of computer hardware. Yeah, although it's quite expensive, there's no one kind of machine that dominates the other. So there are quite a different instruction set. Okay? And designing this instruction set become quite popular, because if you want to build a machine for commercial use, right, you also, any new machine, you have to design instruction set. Therefore, because there are several machines in the market, there are so many instruction sets. And of course, designing instruction sets is a kind of compromising. All right. Therefore, each machine have their strong point and weak point. However, once the industry evolves, right, and we mass produce the processor, and it is impossible to have too much of a different processor to be in the market. Therefore, only two dominate the market right now, and the third one just happening in the last 5 years, right, which is the one we study, which is open core, or a kind of open innovation, that the design and the tools involved to build this chip have been given out to the public. Okay. There are only 3 pages, right? So we will get ourselves involved in these 3 pages. It will concern the instruction in this, on just these 2 pages, not much. Okay. And we use very minimum, because we are using only a certain length, it is word. We'll use the Venus interpreter, okay, as a machine to try on, because it's so convenient. Okay. First task that we study assembly language programming is to move information around, move data around, to move information in the register around. Let's see these 2 instructions. The first one actually move a constant, a small constant, into a register, because it adds that small constant with the register 0, which is always 0. Okay. And when we want to move around, we do the same. By if we want to move this register 2 to register 3, we then use the add instruction by adding with the register 0, and then the information go to register 3. I just copy and pass it in the editor. Okay. We can go to simulator and then assemble it, and the instruction will appear here. I will move my screen around a bit so you can see the value of register. Okay, and we manipulate register number 2, so which is not good, but anyway, we can see number 2, number 3. We try to avoid this kind of registers that have special meaning, but so the first one, we move number 11 to register number 2, so it becomes 11. we can also change this to decimal. You can see number 11 on the register number 2. And then now we move number 2 to number 3, right? We step again. Okay, you can see the effect as we intended. We already moved data from between register. Now we want to move between memory and register. Okay, you use this to instruction to set the value in the memory. So I move number 11. Now number 11 become hexadecimal. Okay, right? We have to get familiar with the hexadecimal, because once they use a compiler to generate machine code, it will generate hexadecimal number. Okay, and then this constant right, in X5 will be stored at the address. We need to use the address that is a bit further away, because remember that we have unified memory between instruction and data. We can always starting at 0 onward. That if you set it at the 0 or 1 or 2 or 3, it will cobble up the instruction. Okay? And the program will destroy itself. Actually, in the real programming, the data will be moved away and separate into 2 separate regions in the memory. It is a normal practice not to allow the instruction memory to be changed. Otherwise, you can create a virus. Okay, you can make change to the instruction itself, right? And then execute it. So you can do whatever you want with it, which is a very high risk for security. We use this kind of addressing. Okay, therefore we have to refer to one register, and we just use that one to be 0. We move it to register from the memory using this kind of load word from memory, and then we want to store it. Therefore, we change the number a little bit and then store them. Okay, now let's see the action of this sequence of code. And we go back to the editor and then pass our code into it. Okay, indentation does not mean anything in assembly language. Okay, let's see how it works. So let's start by executing the first one. Boom. Okay, number 5, and I change it to hexadecimal. Okay, it's 1 in hexadecimal. Okay, and then we store it. Boom. Okay, we can see where it's stored by looking at the memory. Okay, memory 100. Okay, is hexadecimal 11. Then we increment and then store to the next slot in 32-bit. So the next slot is 104 in hexadecimal. Okay, let's see. We increment them and store it. So now we can move things around. Second is we can try to do operation, simplest expression or operation in programming language is to do a kind of simple binary operation and then keep the result into another variable we call assignment. Okay, so with this, okay, we have to make some assumption first, right, about the kind of variable. If this variable is a local one, okay, which is mean we saw in the register, then we have to assume which register we want to use. I want to use 4, 5, 6 as ABC, so it becomes just one instruction. Okay, assuming that the value that we want already stored. So exactly this kind of not bad, very efficient. But this is translated like this because the type or the size of value in the variable is appropriate. So we we imagine that it's all 32-bit. Now, if we assume that the ABC is global memory, so we have to move from the memory and into register and then add them. Okay, so we have to assume ABC in a different manner. Now I assume A is in this is all in hexadecimal now. So 100 and next 104 and then 108. Okay, and the register we want to use is we have to move the information between them. Remember that we cannot add the memory together. We have to get the value from the memory into register and then do the any operation that you want. Okay, so first instruction is to get the B, okay, which is in 104, and then you get the C in 108, and then you add them together, and then you store them in A at 100, right? And just, yeah, it's very simple just to pass it directly like that. Get information from memory, we have to be able to initially set the value somehow, right? Let's say it's 11 in the decimal and 12 in decimal. So when it add together, it becomes 23, right? Let's see. So first of all, we go to the register, and yeah, let's see it in hexadecimal. Now initially it becomes all 0. So the first instruction, get B, which is 11. Okay, so it becomes B. And then second instruction, which we already stepped over it, so it becomes C, and B and C, and then add them together and become in 4, let's see, 4, it becomes 17 in hexadecimal, and then store. Okay, so the last step, and go back to see the memory. Okay, so 17 is here in hexadecimal. Now we want to do a bit more ambitious task, is to manipulate the group of information, okay, so the array. So we need more a way to compute where to get the information from. Okay, let's assume that we have one array of integer. Okay, starting at the 100 address. All right, so we want to get the second element, right, the index 1 of that array. Okay. Remember that the offset is 4, not 1. Okay, and so the way we do it is we will have to compute the effective address where to get the data from the index, okay, and the base. All right. Oh, I got it wrong here. Right? Okay, anyway, let me modify it a bit, because this is the offset I use is 1. Actually, it is 4. If the first element is 0, the second element is index 1. Actually, the offset is 4 bytes. Okay, so it has to be number 4 here. I will correct it later. Okay, and the base is 100, and then we have to add this index and base together. Or let's see, this become a kind of offset. Okay, add them together, and the effective address is stored in register 5, and we use this register 5 to get the value from the memory. I told you I have to change it to number 4, otherwise get it wrong. Okay, and now we run it. Okay, assemble, boom. Before we can really get the value, we should set the value from the memory. It's in some pattern, we have it here. Okay, so let's say, I think it's, let's try some bigger number, right? Maybe, okay, let's try this. Okay, let's try this funny pattern. 1, 2, 3, 4. Okay, so it's a very big number, but go quickly, go run, boom, so it's finished, and we can go to see the value in register immediately at the number 6. Wow, hey, nothing. So what is the effective address we have? Number 5 is 104. Oh, 104. Okay, so no wonder why it doesn't work. Because we set the memory at 1000. Okay, let's try again. I make mistake because this one is the first slot of the array. This is the second one, which index 1. Okay, so yeah, we have 0 there. Therefore, we get 0. Okay, so now we put the constant into the proper memory. Oh no, I have to reset everything, so I have to redo it again. No problem. Go to the editor, okay, to reset everything and come back, and then restart. And the value in the memory also will be reset by the simulator. So let's do it again. 1, 2, 3, 4. Okay, so we have 1, 2, 3, 4 in the memory, and then we can run through. Boom. Okay, and go back to see the value in the register. Okay, X4, X6. Review yourself. Okay, so it have 4, 3, 2, 1 as expected. Okay. Please take a note, right? The number we see from left to right, to the biggest digit to the smallest digit is 4, 3, 2, 1. The way it's stored in the memory is 1, 2, 3, 4. Okay, right, from the lowest memory to the highest memory. Okay, so in the variety of the machine in the past, there are 2 camps. One is so-called little endian, okay, and it is another camp called big endian. Okay, you have to determine the order of multiple bytes, how when you keep in the memory, how it corresponds to the value in the register. Now we know how to move things around, okay, and they get to the array of memory. The next is to do a kind of loop. Let's say we do while loop. Okay, so while loop usually we test some condition and then execute its body if that condition is true. So it becomes a kind of a pseudocode like this. We test the condition, right, and then we jump for if to exit. If the condition is false, then we jump out. Otherwise, we execute the body of the loop, and then we go around again. Okay, you can have a different sequence. Maybe you can jump into test condition can be the end, and then in the beginning you jump into the end. If the condition is true, you jump back to the loop, which will this is, you can see that we have 2 jump in this variety. But if we have a test and jump at the end, we have just 1 jump. For example, we want to go around the loop 10 times, okay, using a variable I. Okay, let's I this become local. Okay, so in the beginning, set the I to 0. Okay, and we have to have some constant to be compared here. Constant has to be in register. To value have to be compared between register. Okay, right. So we have to keep constant 10 in some register. And the main loop, which have 2 jump, is here. Then the first one is to test if the condition is true. If condition is not, this one is, we want it to be less than. Okay, so therefore, if it's false, it has to go to exit. Therefore, we have to change the less than to become greater than or equal. Okay, right. So if it's not true that I less than 10, then it jump to exit. Otherwise, the increment I and jump loop. This is also a shorthand. Okay, when you say J, it means jump without condition, and then the Venus translator will generate the machine code properly for you. And then we go to simulator and then assembly. First, let's see what is a jump look like. So it translates into jump and linked, right? -8, okay. And then but we will not worry too much about jump and link here, but you have to see that is go back 8 byte. So let's start here. Back here is 4 byte. Back here is 8 byte. So it go back to this instruction. Okay. So therefore, it's the body of the loop, and it tests again. And this one, if it become false or it's not I less than 10, then it jump to 12. So 12 is 4, 8, 12 is outside. It jump over the last instruction. So the end result is the index reach number 10. Now we put in some real program, so to speak, rather than a fragment. And what we want to do is to have a set of number in an array, and we want to add them add the value of our element together. Okay. Oh, and I get it. Okay, so the pseudocode, whatever high-level language you are familiar with. Okay, so first we reset the sum and the index. Okay, this is a bit tricky. Okay, because the index is increment by 1. Okay, in actual high-level language programming, but when we want to access the actual memory in 32-bit format, we have to increment by 4. Okay. Okay. So the code is self-explained. No need to worry. And we sort of have to assign everything, which register we want to use. This line is very important. Kind of you have to make note, otherwise you get confused by the number of register. Okay. So we have local variable s and I. So we did that. So we did 3 and 4. Okay. And we need some constant. So we also need that. We use register 5. And then we need also the base address of the array. So we also use that. Okay. And then we have to compute the effective address. We use another register for that. And as I told you, the offset has to be incremented by 4. So we cannot rely on I to be the actual offset. We use I just to test the loop that it's reached the end. Okay. So we have to compute the offset using another register. So we use it here. And we also have to get the value, okay, of the element in the array. So we have to use another register. Okay. Right. Let's see how it works. So this is the kind of one of the one. So you can see the body of the loop. So in the beginning, we just initialize the value of various registers. So we set the S to 0 here. Okay, we set I to 0 here. We set the constant 5 here. And then we set the base address here. Okay, so it's all set. And we start with the offset 0. Okay, to check, okay, if the I less than 5 is true. If it's false, then we jump out. And the body of the loop is, first of all, we have to compute effective address, similarly to our previous example above, right? So we add the base to the offset, right? Not the index, the offset, because the offset have to be incremented by each time by 4. So we compute the effective address and use that effective address to load the value of the element of array, okay? And then sum it up here, right? And then to get to the next element, we have to increment the offset, okay, right? And then we increment the index I, so it can check the repeat of the loop is 5 times. and we jump loop, very proper. We go to the simulator, assemble them. Okay, before we begin, we should really set the memory. Okay, otherwise we will have the result 0 again. Okay, so go see memory, and it's stored at 100, 5 elemental 0, 1, 2, 3, 4. Okay, right. So let's say we add number 1, number 2, number 3, number 4, and number 5 here. Okay, so we actually add 1, 2, 3, 4, 5 together. All right. So the result should be in register 3. Maybe we go through the loop just one more time and then run through the rest. Okay, so we set all the register by the first 4 or 5 instruction and see if the all. So 3, 4 should be 0. 3, 4 should be 0. It is 0. And 5 should be 5. 5 is 5. 6 should be big. Okay, so 100 a base address of our array in number 6 properly, and offset should be 0, number 80. Okay, so every register has been set properly, and the next step is to check the loop. Okay, condition the loop. Okay, and we go through the body. The body is a compute effective address. So the first effective address is the first slot. So once it compute, it becomes 100, but at the x7. Okay, it's correct. And then we get the value, the first value, into register 9, which the first value is 1. Register 9, let me scroll up a bit. Yeah, it's 1. So the first value here. And then we step through, and then now we increment the offset to the second element. It should be 4. Okay, so the next offset is the first, the second element is 4, right? And then we increment the I, reason number 4. Boom. Okay, I become 1, and then we jump back, right? Jump back to the condition. Okay, now I can just run through and see the result. The result, we have the result in register 3. Okay, so we can boom, and it's terminate and exit. And x3 is the value 1, 2, 3, 4, 5. Add up with 16, so 15. So it become 0f. We can check that using decimal. Okay, the value in decimal is 15. Oh, that's well and good. So